That's like how we got it.
Okay. So let's finish off our section on subsequence regret. So just to remind everyone where we are and what we've done. For the last 3 or 4 lectures, we've been talking about multi-objective optimization problems. Okay, initially in the very abstract. There's not just one thing you care about, there's D things you care about. The way those things manifest themselves is that at every round, you've got like D loss functions. You play some action at each round, the adversary plays some action. You get loss in each of these D coordinates. They accumulate over time. And how sad you are at the end depends on the value of the maximum coordinates of these accumulated losses. Okay, so that was a very abstract setting. And we instantiated this in the last few lectures in a particular way to get more sophisticated regret kinds of bounds, regret bounds that we called subsequence regret bounds. So the things you cared about were always your cumulative performance in some online linear optimization game, except not just overall summed over all of the rounds of interaction, but summed over different subsequences of the rounds. Okay, and because you cared about more than one subsequence, there were more than one thing you sort of cared about, and we fit that into this multi-objective optimization framework in a pretty natural way. Like in particular, we said, okay, well, there's a set of events that you care about, and subject to each of the events, you'd like to have no regret to each of your actions. So we're like, all right, you know, let's say that there's a coordinate of the loss function for each pair of events that you care about and action. And what's the, you know, if you play some distribution over actions and the adversary picks some cost vector, well, how much loss do you experience in the coordinate corresponding to some event and some action? Well, it's just your instantaneous regret to that action if the event is active today. Okay, so remember these events, they can depend on the history, they can depend on external context, and they can depend on the action that you play. Okay, and so like the loss corresponding to some event and action I, if you play some distribution P and the adversary plays a cost vector C, is the indicator of whether the event is active or not. Okay, so if the event's not active, 0 loss in this coordinate, it doesn't contribute to that event. Otherwise, it's the difference between the cost you experience, the cost of the action you play, and the cost of action I. So it's just sort of like your conditional instantaneous regret to action I, given that you played action J and the event was active. Okay. Now, in general, like we had like a general algorithm for this multi-objective optimization framework that you know, applied quite generally, but sort of had what was sort of a pretty non-trivial, like expensive step at the end here, which was computing a minimax equilibrium of some game. Like you have to solve, you know, like unlike multiplicative weights or something where there's just a distribution you're maintaining that you play, you know, like in the general multi-objective optimization framework, there's an optimization problem to solve, a non-trivial optimization problem, a min-max problem. Okay, what was it? It was, you know, like min-max optimization in a particular zero-sum game whose objective happened to be defined by some linear combination of the loss increments at this round, weighted by what? Well, weighted by exponential weights. Okay. And then last class, we were like, all right, well, you know, it's sort of annoying if we need to solve this optimization problem in every round. Maybe we can get sort of a, you know, like for multiplicative weights, like a closed form kind of solution. And we did for the particular special case of subsequences that happened, even though in generality, subsequence indicators can depend on the action that you play, we derived sort of a closed form last class for the special case where they happen not to. We called these action independent subsequences, and they captured actually like a bunch of interesting stuff. It captured adaptive regret. So if you want regret on every contiguous subsequence, that's action independent. It covered groupwise regret. If you want regret conditional on any function really of the features that make up the external context, that's action independent regret. And the algorithm was actually pretty simple and natural. It sort of looked like maintaining a multiplicative weights distribution for each of the subsequences, sort of the distribution you would have maintained had you run multiplicative weights only on examples that activated this particular subsequence. And of course, you can't do that because examples simultaneously can activate multiple subsequences. And so what do you do when such an example arrives? Well, you just take all of the subsequences that are currently active. This is something that's well defined because the subsequences do not depend on your action. Okay, you take all of the subsequences that are currently active, which in this case you happen to know before the round begins. You sum up those distributions, you normalize, and you play proportional to that. And that's it. Okay, so simple closed form solution. You can sort of do simple multiplicative updates the same way you do with multiplicative weights. The overhead is, just sort of a factor of how many subsequences can be active at any particular round. That's how many of these copies of multiplicative weights you ever need to update at one round or add together. So it's good, but it didn't cover everything. Like in particular, like in order for this algorithm to even make sense, it really like depended on the fact that these subsequences were action independent, right? Because like even for me to say sum together the distributions corresponding to those subsequences that are active today and then play that distribution requires that before I decide what I'm going to play today, I know which of the subsequences are active. But if the thing that I play determines whether the subsequences are active, then there's this sort of self-referential problem that sort of we're going to need to resolve. Okay, and although action-independent subsequences captured lots of interesting stuff, it didn't capture everything. In particular, it didn't capture swap regret, this thing that was sort of the motivating story for this whole sequence, right? Like if we can get algorithms that guarantee players diminishing swap regret, we can get convergence to correlated equilibria in general games. But swap regret basically follows from having no regret on each of the k subsequences corresponding to rounds on which I played action k. So these are subsequences that depend on what I play, and so they fall outside of the framework we've covered. And so what I want to do today is I want to derive an algorithm for not just action independent subsequences, but sort of a general algorithm for getting diminishing regret on any polynomial collection of subsequences that are allowed to depend on the actions. Okay, this will include in particular swap regret. That is sort of easier to implement than this in general. Okay. Now, just like the algorithm we derived last class, what we're going to do today, you shouldn't think of it as a new algorithm. You should think of it as an implementation of this general algorithm, right? Like, how did we derive the algorithm from last class? Well, really, we just sort of characterized what this min-max strategy looked like. The algorithm from last class, it wasn't a new algorithm, it was this algorithm. We just figured out what the min-max solution had to look like, and that was the more efficient algorithm. Okay, so we're going to do the same thing today. We're just going to, in a more general case, figure out, by thinking about the game, what this min-max solution has to look like, and play that. So it's not going to be a new algorithm. It's going to be this algorithm. We're just going to use structure of the problem. Am I back? Yes. All right. New batteries in my thing. Okay, so we're gonna, for general subsequences, including action-dependent ones, try to get a more efficient version of this algorithm by characterizing what this min-max object looks like. By the way, if you've seen swap regret algorithms before, maybe because you took my nets 412 class and we gave one, if you were like me, they kind of look like magic the first time you see them. Like what, if you haven't seen them before, don't worry about this. You'll see it in a moment. But like, the algorithm that we're gonna analyze and that you may have seen before looks really weird. You like write down some matrix, you take a top eigenvector of the matrix, and like that's somehow the distribution you play. And like, in nets 412, like we sort of have this magical analysis that post hoc, shows that this works. But for me at least, like this was always magic. Like, how would you come up with this algorithm? And we're going to derive it from first principles. This algorithm is the equilibrium strategy of this game. Okay. Okay. So what is the algorithm? Where did my special chalk go? Okay, so here's an algorithm for getting diminishing subsequence regret in general, not just for action-independent subsequences. Okay, so we're given a collection E of M subsequence indicators. Yes, you can. This thing. Yeah. We want an implementation of this algorithm. So yeah, like I want basically something that's more efficient than this. This requires that at every round you solve a minimax equilibrium, which you can do. I mean, it's a I guess E times D dimensional linear program. You could just solve a linear program at every iteration. I just want something more efficient than that. But you're right. So like in some sense, like also for last class, right? For these subsequence independent, these action independent subsequences, you could have just run this algorithm. I mean, it was just an implementation of this algorithm. All of this follows from this algorithm. We're just noting that in particular special cases, the equilibrium has like a nice structure. But yeah, I mean, the thing I'm going to write over there is this algorithm, just in a different form. Okay. Okay, so we have our subsequence indicator functions. What do we do? Well, for each of t rounds, we observe the context. And now we're gonna do something that looks kind of similar at first to what we do for action-independent subsequences. We're gonna define a closed form weight for every event expert pair. Okay, so for each event and for each action, define the following weights. Okay. Weight at round t corresponding to event E and action I. Okay, so there's m times k of these numbers. And they're going to look sort of like these, multiplicative weights, kinds of weights. So in the numerator, we'll have the exponential of eta over 2 times the sum over all previous rounds of the expectation over the draw of our action at these previous rounds of the subsequence regret. So, the indicator that subsequence E was active at round T prime times the regret to action I that we experienced at that round. Okay, so this is just in the numerator, the exponential of the cumulative subsequence regret we've experienced so far to action I for subsequence E. Okay, so it's like the multiplicative weights kind of weight if we were running only on that subsequence. Okay, and there's going to be a denominator too. It's going to be the sum now over all events E prime and experts J, something that looks kind of similar, e to the eta over 2 times the sum over all previous rounds of, again, the expectation over actions sampled from our strategies at those previous rounds of the indicator for whether subsequence E was active, subsequence, I guess, E prime was active. Times our regret of action J. Okay, so far so good. We're defining weights. This is sort of how we started deriving algorithms for the action-independent case. What we did next was we sort of summed up the weights for all of the subsequences that were currently active. We can't do that now because we don't know what subsequences are active because that depends on what we apply. So here's where we're going to start to do something that, like the first time you see it, kind of looks like magic. So we'll define a K by K matrix A. Okay, what are the entries in this K by K matrix? Well, entry Aij is going to be, we'll have in the numerator, the sum over all of the events E of the weight that we just computed for event E and action J of the indicator telling us whether event E would be active today were we to play action I. Okay, what's in the denominator? The sum over all actions I prime and over all events E of the weight that we computed for event E and action I prime of the indicator that the event E would be active were we to play action J. Okay, so this is a matrix indexed by like a pair of actions. Okay, and in the numerator, we're talking about whether the event E is active if we play action I. In the denominator, we're talking about whether the event E is active if we play action J. Okay, but it's some K by K matrix. And then we'll let PT, the thing we're actually going to play today, be some distribution over K actions, satisfying what? Satisfying the matrix equation A dot PT equals PT. Okay, so this is an eigenvector of this matrix with eigenvalue 1. And a priori, it's not clear this should even exist. Like, we defined some matrix. We need we need this matrix to have an eigenvector with eigenvalue 1 that also happens to be a probability distribution. In general, that won't happen, right? Like, we need all of the entries to be like real valued. We need them to be, non-negative. We need them to, well, I guess summing to 1 is sort of without loss of generality. But you need them to be like non-negative. Okay, so not clear that should even exist. Not clear why we would do this. Why are we, like taking an eigenvector of a matrix? Okay, but the claim is that's what you do. And the distribution you play at the end is not the distribution defined directly by these weights, which is sort of what we do for action-independent subsequence, but somehow a distribution which we'll have to prove actually exists that happens to be the top eigenvector of the matrix that comes from stacking these weights on top of each other. Yeah. Well, so right now I've just written a magical algorithm on the board. I haven't derived it yet. That's right. So like, yes. So at the moment, like, if you're me at least, you see this algorithm and you're like, what the heck? Like, why are you taking like where did eigenvectors come from? We haven't done any linear algebra in this whole class. We're solving like a min-max optimization problem normally. Like, what is happening here? Okay, so the theorem I want to prove today, which is that this algorithm is this algorithm, and therefore gets the nice subsequence regret bounds we've already proven. The way I'm going to prove it is by starting from this algorithm and thinking about what the min-max equilibrium must look like and arriving at this algorithm. Okay, so like, if you understand, like, if the min-max stuff made sense to you, if you sort of understand why this is a good thing to do, then hopefully by the end of the class you will understand why this is a good thing to do, because this, I'm claiming, is like, in closed form, the solution to this particular min-max equilibrium. Does that make sense? Yeah. That's right. So these subsequences can be arbitrary as we've defined them. So it can be any number m of subsequences. Doesn't have to be like the swap regret ones, for example. They can depend in arbitrary ways on the history, the context, and the action you're playing. That's right. Like, the numbers in the matrix are derived from, they're computed here. So like, yeah, the running time of this thing, like, you're gonna need to at least compute each of these numbers, and so that'll take time. M cross k, or m times k, just to compute the numbers involved here. Okay. So does the thing we want to do make sense? Is the algorithm? It's okay if the algorithm looks weird, but is it at least like well defined in your minds? It's clear what this algorithm is. Well, yeah. I guess you might worry about this step. Maybe this doesn't exist, but like, we'll prove it does. But like, it's clear that like, if there is such a distribution P, then like, in principle, you could like implement this algorithm. Yeah.
Like, you just like intuition briefly again for like the min-max problem. There's a thing that we're finding, and we have these weights, and how can I think of these weights? Like these CIs.
How should you think of them? Well, these are the weights maintained by like the exponential weights algorithm. The intuition here is that the exponential weights algorithm is like betting on you to do badly. So it's putting more weight on objective values that you historically have done badly on. And the no regret guarantee of exponential weights is that the cumulative gain of exponential weights will be nearly as large as the magnitude of the worst case accumulated loss in all of the coordinates. And what we are minimizing is the per round gain of multiplicative weights. And so if we can make sure that the per round gain of multiplicative weights is small, then the cumulative gain of multiplicative weights will be small. And by its regret bound, the cumulative loss we have in the maximum over any of our coordinates will be small. That's how we derive that algorithm. Okay, all good so far? Okay. Okay, so the theorem is that these two algorithms on the left-hand side of the board and the right-hand side of the board are the same algorithm. Okay, and in particular, like that's going to imply that, since we already proved a subsequence regret bound for this algorithm, that if we look at the maximum over all of the events and over all of the actions I, our cumulative regret in the end on subsequence E to action I will be upper bounded by 4 root T log the number of subsequences plus log the number of actions. Okay, this is just the subsequence regret bound we proved for this algorithm. Okay, but we're not going to be dealing in regret bounds. We already proved a regret bound for this algorithm. The thing we're going to show is that this is just an implementation of that algorithm. In particular, we're going to sort of work backwards. We're going to start from this algorithm. We're going to we're going to just think about what the sort of min-max optimality conditions must imply about the solution. We're going to use the fact, by the way, that we know that the value of the game, the subsequence regret game, is 0. Okay, which is going to be important. Like that's ultimately going to be the fact that's going to give us existence of such a distribution P. Okay, so just maybe like marshalling the things we know. We know that in the subsequence regret game, okay, defined by this particular multi-objective encoding, the adversary moves first value is 0, which just means if the adversary tells us what their cost vector is, we can just turn around and deterministically play the action that has the smallest cost, and our instantaneous regret in every coordinate will be at most 0. Okay, which means that the value of this zero-sum game, to which the min-max theorem applies, is 0. Okay, that's going to be something we already know about this game and is going to be like an important fact in our derivation here. Okay. Okay, so what do we need to do? We need to understand what the min-max equilibrium looks like for the game whose utility function, I'm just going to rewrite this utility function with the particular choices we've made for what the losses look like. Okay, so for the game with utility function that looks like the following. Okay, we have the sum over all of the coordinates. Well, what is that in the subsequence regret game? There's one coordinate for each subsequence indicator function and for each action I. What is in that coordinate? Well, since I'm using P now for the action space of the learner, rather than calling these weights P, I'll call them W. Okay. So we've got some weight on each coordinate. And the weight is multiplying the loss increment in that coordinate. Well, what's the loss increment in the subsequence regret game? Well, it's just for subsequence E and action I. It is just the expectation over the draw of our action from our distribution P of the indicator that subsequence E is active today times the difference between the cost of the action we play and the cost of action I. Where, you know, the weights, I already have them written down somewhere. Are they just these? Yeah, where the weights are these things. Okay, so it's these weights. Okay, so this is sort of, yeah, we're finding a min-max equilibrium of this. Here we've instantiated the general thing with our particular loss functions. The hope is that the structure of our particular loss functions is what's going to give us sort of a more specific algorithm. So let's try to exploit that structure. Let's play with the form of this expression. Okay. So maybe the first thing we might do is, you know, we've got like a sum here and we've got like an expectation here, but an expectation is really just a sum. So let's turn it into a sum so that we can play tricks by like exchanging summations and changing the names of variables and all of our favorite algebraic manipulations. Okay. This is the utility function of the game that this algorithm is computing the min-max equilibrium. It's the expression within the min-max, just specialized to our setting. So those weights P there, in our setting, it's these weights W. And the generic loss function there, in our setting, it's the loss increments for the subsequence regret game. Okay, so what we need to understand is what the min-max equilibrium of this game looks like. Does that make sense? Okay. Okay, so let's just sort of turn this expectation like into a sum, just so that everything's on the same footing. Okay, so we're really summing over three things. It's the sum over actions I, and then again the sum over actions J, and then the sum over events E of, well, the weight corresponding to event E and action I times, well, what was this expectation? It was the sum over actions J of the probability that we play that action J times the thing that's inside the expectation operator. So times Pj, that's the probability we play action J, times the thing inside the expectation operator, times E, yeah, the indicator function for the event when we play action J, times Cj minus Ci. Okay, so it's really just three sums. Okay, and now I sort of want to use that there's like a certain amount of symmetry here, right? Like there's a difference here between, all of this stuff multiplied by Cj minus all of this stuff multiplied by Ci. And there's really not that much difference between J and I. J and I are both just sort of indices of summation that are both going over all of the actions. Okay, so it doesn't really matter that we called them different things. So I just want to break this up into a difference of two summations. And along the way, I'm going to perform like a little sneaky change of variables. I'll point it out when I do it. Okay. So, okay, the first term, all right, like it's just Cj times all of this stuff. So what's the first term look like? Well, the sum over all of the actions I of the sum over all of the actions j of the sum over all of the events E of the weight for event E and action I times the indicator for the event when we play action J times PJ times CJ. Okay, so all I've done so far is just sort of multiplied all of this through by CJ. Okay. Minus, I'm just going to like write the whole thing again, multiplying all of this through by CI. Okay, but in this second sum, I'm going to rename my variables I and J so that the thing I previously called I, I'm now going to call J, and the thing I previously called J, I'm now going to call I. It's like totally fair game. Like I and J are both summing up over the same indices. It doesn't, nobody cares whether the name of the variable is I or J or alpha or kappa or whatever. I'm just going to like rename the variables. Okay, so now I'm going to like expand this whole thing out again. It's the term multiplied by minus Ci, except I'm going to call it minus Cj, and wherever J was written here, I'm going to call that I. Okay, so I'm subtracting off again the sum over I, the sum over J, the sum over E of W, the weight assigned to event E and action J. Remember, I'm renaming I J and J I. So make sure I swap I for J and J for I every time over here. Times the indicator of the event when I play action I times PI times CJ. Okay. So all I've done is I've expanded out this expression to the difference between two sums. And like the one sneaky trick I pulled is in this sum, I renamed what was, the letter previously known as I, J, and the letter previously known as J is now I. Okay? It's like not too sneaky, just rename some letters. Okay. Good. I want to rewrite this one more time by pulling out Cj. I'm going to factor out Cj. And the point of doing this is I want to sort of separate out terms that depend on the adversary. Okay, the adversary just chooses the C's from terms that depend only on the learner. The learner chooses the P's. Okay. So I can actually, I can write this just by pulling out Cj. Right, I'll just sum over actions J first of Cj times, okay, Cj will multiply all of this stuff, right? Because we have a Cj times this stuff minus Cj times this stuff times the sum over all of the actions I of the sum over all of the events E of the weight we assign to event E and action I, of the indicator that event E is active when we play action J, minus the sum over all of the actions I, of the sum over all of the events E, of the weight we assign to event E and action J, of the indicator that event E is active when we play action I. I guess this one was multiplied by Pj, and this one was multiplied by Pi. Okay, so nothing has happened except I have just factored out Cj. But what I want to note is that this big expression inside the parentheses does not depend on Cj. It only depends on P, right? It only depends on the action of the learner. The adversary's action sort of is relevant only in that it provides the multiplier for this thing. Okay, so let me just get, so that I don't have to write out this expression too many more times, let me give it a name. The thing inside the parentheses, I'll call it chi Tj of P. Okay, so this expression depends on the index J, so it's indexed by J. It is a function of the learner's strategy P, but it does not depend on C. Okay? Good. Okay. The upshot of, this algebra is what? It is that I can write the utility function, this whole thing, as just, in our now more concise notation, the sum over all of the actions from 1 to k of Cj times chi j of P. Okay, so it's actually a sort of nice factorization. This expression chi, maybe it's a little complicated, but it only depends on the learner's action. The adversary's action serves only to provide the multipliers for these expressions chi. Okay, this is something that's like not true in general, but happens to be true of this utility function, and we sort of took advantage of the symmetry here. Okay, so this is the structure that we're going to want to use. Okay. Okay, so we know that the value of the game is 0. Yeah.
It's linear, it's separately linear, adversary action, learner action, idea of the.
That's, yes, that's sort of what we've derived. Separated these things out and used the fact that there were these symmetries so that I could rename I and J, basically. Okay, right, like everything here was just pure algebraic manipulation. The only possible cleverness was the change of variables, okay, to get things into this form. Okay, and now I'm gonna use the structure that comes from the utility function being in this form. It's separably linear, as you say, and I know that for this particular game, the value of the game is 0. Because that's something we've argued previously, and it's also easy to see directly from sort of these regret losses. If I know what the costs are ahead of time, I play the lowest cost action. My instantaneous regret for each event is non-positive. Yeah.
Follow up. Normal form games that we're talking about, it be a completely obvious statement that losses whatever separately linear. It's only, but it's not obvious that it's not a normal form case because the adversity clause is not quite distributed. The adversity is actually stated.
Yeah, the adversary has like a continuous action space.
Yeah, and you can still.
That's right. Yeah, so yeah, possibly you have like a less painful way to get to this point. Like this is the structure we're going to use. Okay, good. Okay. So since we know that the value of the game is 0, we know the property that you know a minimax. We know a property that a minimax equilibrium of this game must satisfy. Okay, so what this means is that some distribution P star is a minimax strategy. If and only if, and this is like the definition of a minimax strategy when the value of the game is 0, if and only if for every cost vector simultaneously, okay, so for every vector C that assigns to each of its coordinates a number between 0 and 1, the utility in this game when we play the minimax strategy and the adversary plays C, which again is just the sum over J of Cj chi j of P star. This has got to be at most 0. Right, like that's just the definition of a minimax strategy. If you play your minimax strategy, then no matter what your opponent does, in particular simultaneously for any action of your opponent, you have to obtain at least the value of the game, and the value of the game in this case is 0. Okay. Okay, so like in particular, we must have, it must be that simultaneously for every coordinate j, this expression chi t of j when evaluated at P star has got to be at most 0, right? It's got to be, right, like if you know, the weighted sum of these things has to be at most 0 for every weighting, they've all got to be at most 0, right? Because if there was any one of them that was positive, right, if there was any one of these terms that was positive, the adversary would pick a weighting that put weight 1 on the positive one and 0 everywhere else, and that would be a C such that their weighted sum was bigger than 0, which we just said can't happen. Okay, so in particular, since we know that a minimax equilibrium strategy must make this weighted sum less than 0 simultaneously for every non-negative weighting, it has to be that pointwise, a minimax equilibrium strategy makes each of these expressions at most 0. Okay, that gives us some structure. Like we have, you know, we know that, you know, this gives us like some inequalities, right? Like we know that here's some expression, it's got to be like at most 0 for every P star. We could try to find P stars that satisfy that expression, but maybe we still have some wiggle room, right? Like maybe, you know, like, yeah, maybe there's more than one way to satisfy these inequalities. Okay, but like there's something else we know. If we sum up over all of the j's of chi j of P for any P, I claim this is always going to be exactly 0. And that follows from symmetry. Like, what is chi j of P? It is the difference between these two sums. They sort of differ in what they are indexing. Here, I is indexing the weight over here, but not the event in here, or PJ. Here, I is indexing the other thing. I is indexing the event in here and PI, but not the weight. Okay, so these two expressions are different. But if we sum up over all J, then both of the expressions are the same. We're summing up over both of the variables I and J of the same expression. Okay, so if we, for any distribution, if we sum up over all of the J's of this expression, we have something minus the same thing. So it's 0. Okay. Okay, so what do we know? Well, for any distribution, the sum of these chi-j's is 0. Also, for a minimax equilibrium strategy, none of them are positive. Okay, so how can both of those things be true? It must be that for a minimax equilibrium strategy, chi-j of p star is actually exactly equal to 0 for all j. Right? If if the sum of them is 0, then if some of them were strictly less than 0, others of them would have to be strictly greater than 0, and that's not allowed. So if they're all less than 0 and the sum is 0, they're all 0. Okay, so that gets rid of the wiggle room. Now these are equalities. Okay, so this is what we're gonna use to pry out what the equilibrium strategy has to look like. That's right. So let's see what's let's see where this takes us. Okay. So let's see what happens when we just write down this expression. Okay, we know what chi-j of p is. Okay. Okay, so in particular, the claim is when we plug in p star for p, so when we put stars here, the claim is this expression is going to have to equal 0. And so let's just try, set this equal to 0 and then isolate pj star. Let's just get an expression for pj star. Okay, so pj star, just by setting this thing to be 0. What does it mean to set this thing to be 0? We set this thing to be 0. How do we solve for pj star? Well, we add this expression to both sides and then divide by this expression. Okay, so let's do it. pj star must equal the sum over all of the actions of the sum over all of the events of the weight of that event times the indicator that that event is active when we play action I times pi star. Okay, that is just this part of it. Okay, divided by this part of it. Okay, so divided by the sum over all of the actions of the sum over all of the events of the weight of that action, the weight of event E and action I, of the indicator that event E is active when we play action J. Because I'm setting this whole thing to 0 and solving for pj. So how do I do that? I bring this expression to the right-hand side by adding it. That's the numerator. And then I isolate pj by dividing by the thing that is multiplying it, which is the denominator. Good. Okay. I guess that thing kind of looks familiar, right? Like we've got these like matrix entries here that we're kind of. That's the thing. P star is the vector we're trying to solve for. Okay. Now it just so happens that this matrix has been defined so that writing this in matrix form is just A times P star equals P star. Okay, it's top eigenvector of a matrix. Now, okay, remember, like a priori, it's not clear that such a thing exists. But since we know the value of the game is 0, and we know that the minmax theorem is satisfied by this game, and we know that every minmax strategy must satisfy this identity, which is equal to this identity, we know that there must be a solution to this, right? Like if there wasn't a solution to this, that would mean that the min-max value of the game wasn't 0, but it is. Okay, so in some sense, we're proving that the matrix must have an eigenvector with, eigenvalue 1 that happens to be a distribution, essentially by the min-max theorem and the fact that this particular game has value 0. Like there would be no, it wouldn't have had value 0 if this matrix didn't have this eigenvector, because any min-max strategy must satisfy this matrix equation, and there is a min-max strategy with value 0. Okay, and so that's it. We just derived this algorithm. It's the equilibrium of this game. Yeah. Yeah, it's also like the fact that it's the transition matrix of a stationary distribution. Sorry, it's the stationary distribution of a transition matrix. That's true for like swap regret, but I'm not sure that's actually true for all subsequence regrets. So it's like, yeah, this part, maybe is worth thinking about. I haven't, but like the Blum Mansour algorithm happens to give you the sort of, the matrix A is the transition matrix of a Markov chain. There's a steady state distribution, and so there's this sort of other theorem that tells you that P star must exist. But I don't think that argument generalizes to other. I think it might depend on what the events look like. I was sort of thinking about this for a while and kind of gave up at some point. So there might be some structure here that I just haven't seen. But without knowing what the events look like, I'm not sure this is always a stochastic matrix. But there's always, the matrix we need is always going to have the eigenvector we need, because the min-max equilibrium condition requires it.
Is there any intuitive explanation of this that is like more linear algebraic?
More linear algebraic than taking the eigenvector of a matrix.
Or the thing is, like, that part, that I don't know.
Yeah, I mean, let's see. I don't know. I mean, like it just happens.
It's like the rest of it. Right after, like, oh, this equation will.
Yeah, that's right. Like somehow, like for this particular game, you write out the constraints that are imposed by min-max equilibrium conditions, and it happens that the thing that pops out is the top eigenvector of a matrix, which is interesting. Well, maybe it's interesting because it tells you something about the structure of the solution, but also for computational reasons. Rather than solving an arbitrary linear program, you just need to take the top eigenvector of a matrix. Yeah. I was hoping nobody would ask that question. I don't know, but it seems like it shouldn't be too bad. Like you can, I don't know, approximate it with the power method. But yeah, I mean, this is, I'm sure, the topic of like intense study probably 50 years ago in sort of numeric computation. But yeah, I don't know what is the like running time of the best algorithm for computing the top eigenvector of a matrix. I'm pretty sure it's better that, well, oh, definitely polynomial. And I'm pretty sure it's better than the running time of solving an arbitrary linear program. Yeah, otherwise this whole lecture was dumb. We should have just stuck with that. Yeah, I mean, it's really, actually, and since you already know that, it's really just solving a system of linear equations, right? So it's rather than solving an arbitrary linear program, here, this is just a system of linear equations, which you can do with Gaussian elimination. Yeah. I don't know the complexity of that either, but it feels easy. You know, you did it in grade school. Yeah, that's a good question. Yeah, that's a good question though. Like concretely, right? Like how much more efficient is this than just directly solving the min-max computation? I'm not sure exactly. I'm like hoping this is more. You've actually implemented this algorithm, right? Like how does it, well, how long does it take?
Like when I call like and not whatever the part of it, fine.
There you, okay. There you go. Yeah. Yeah. Anyways. That's right. So to write down this matrix, you need to enumerate over all of the events. So like this will work not just for, you know, we're going to sort of note in a moment that this is going to give us a swap regret bound, right? Just a few i's to dot and t's to cross there. But this works not just for swap regret, but for arbitrary subsequences. And in general, if you have a lot of subsequences, the dominant time here is going to be in writing down this matrix, which will, even though the matrix is only k by k, the numbers in the matrix require summing up over all of the events and computing something for each of the events. Okay, good. Anyways, for me, yeah, like it was useful for me to see this derivation to understand like where this funny algorithm comes from. Okay. All right. So well, let's sort of come full circle and just wrap up this section of the course. So remember, our motivating problem when we started studying subsequence regret in the first place, it was to compute correlated equilibria in games. It was to have sort of a dynamic that would converge to correlated equilibria in like arbitrary games. And we noted that there was sort of this equivalence between play of the, you know, the empirical average play of the game being an approximate correlated equilibrium, and each player in that game having diminishing swap regret. Okay, so let's remember what swap regret is. Swap regret is not immediately it's not like immediately obvious that swap regret has anything to do with subsequence regret, right? There's no direct mention of subsequences when we talk about swap regret. Okay, so what we noted at the beginning of this section of the course is that the empirical play formed an epsilon approximate correlated equilibrium. If and only if, for each player I, their swap regret was bounded by epsilon t. So what was their swap regret? It was the maximum over all strategy modification rules, all mappings from the action set of player I to other action sets. Okay, so yeah, maybe I went and I played the game, and I had some payoff, and like ex post, you're like, like when you played action 3, you should have played action 7. When you played action 4, that was good. You should have kept, you made the right decision there. When you played action 5, you should have played action 9, right? Someone who sort of looks over your shoulder and then, with the benefit of hindsight, kind of makes corrections. But the granularity of those corrections are not at individual days, but are sort of on categories of things you've played. Okay, so they propose some strategy modification rule you should have played, and they compare cumulatively over all time what your loss was given what you actually played compared to what your loss would have been had you, applied their strategy modification rule, easy for them to say, and everyone else had stayed fixed. Okay, this is swap regret. If this whole thing was bounded by epsilon t for every player, then the empirical play over these action profiles was an epsilon approximate correlated equilibrium. Okay, so that was our starting motivation. We were like, all right, we'd like to be able to converge to correlated equilibria in arbitrary games. We know how to get no external regret. If only we could come up with algorithms that got no swap regret, we'd be done. Okay, and now we just spent, however many lectures building up all of this machinery for subsequence regret, culminating with this, like matrix computation thing. Like, have we solved our problem? Okay, and it's maybe not like immediately clear because, subsequence regret it's like the maximum over like subsequences of the regret on the subsequence of rounds indicated by the subsequence indicator function. Whereas here we're taking a maximum over strategy modification rules. By the way, there's truly a lot of these, right? There's k to the k of them, because for each of the k actions you could have played, there are k different things that this annoying backseat driver could have suggested would have been a better idea to play. Okay, there's a lot of strategy modification rules. Okay, so we need to like understand how swap regret maps on to subsequence regret. So let me, as an intermediate step, define something called internal regret, which will just be transparently a special case of subsequence regret. So a learner has internal regret alpha if they have subsequence regret alpha on the collection of subsequences that I'll call, the internal regret collection. What are these? Well, there's one such subsequence function. I'll call it EA for each of the actions available to the learner. And each of these is a pretty simple subsequence function. It doesn't depend on any context. It doesn't depend on the time step. It only depends on the action played today. So it is the sort of subsequence that depends on the actions. We need the algorithm we derived today. And it is just the indicator function that the action you played today was actually action A. Okay, so it's one subsequence for each of your actions. It is active, it identifies the subsequence of rounds for which you played action 1. Another one identifies the subsequence of rounds for which you played action 2. Another one identifies the subsequence of rounds for which you played action 3. There's K of these subsequences. Okay, so there's not that many. We can minimize internal regret as a immediate corollary of our subsequence regret algorithm. Okay, just maybe sort of writing this down more directly, just explicitly writing out the definition of subsequence regret for these subsequences. What we require, and what this means, is that for all of our actions I, the sum for all of our actions I, and also for all events A. What we require is that summed over all of the rounds of the probability that we play events A at that round times our regret, given that we play action A, our regret to action I, this should be bounded by alpha. Okay, so internal regret alpha just means we should have no regret on any of the subsequences for which we played action A, for any of our actions A. What does subsequence regret mean for this collection of subsequences? It just means for every action A, and any other action I we might have regretted playing instead of action A, summed over all of the rounds of the probability that we play action A times the difference between the cost we would experience if we played action A minus the cost we would have experienced if we played action I, that should be small. Even on those rounds when we played action A, we shouldn't have been able to do much better by playing I instead. Okay. Okay.
Applies on every action A?
Simultaneously for every action A. Yeah. So this is the statement that we have no subsequence regret on the subsequence defined by action A, and we need no subsequence regret for any of the actions A. Okay. So one observation is that if we have internal regret, alpha, we have swap regret at most k times alpha. Or said another way, for every strategy modification rule, mapping our actions to themselves, if I sum up overall time and look at in expectation over my play, the difference in cost that I would have experienced had I made no modifications, and compared that to the difference in cost I would have experienced if I had gone and applied my strategy modification rule to the actions that I sampled instead. Okay, my realized regret for not having played this strategy modification rule, that this will be bounded by at most k times alpha. Okay. Yeah, you can get a root k if you are more careful. The way to be more careful is to basically prove a better subsequence regret bound. Like at the moment, this is related to like things we've talked about before. So like at the moment, what we're doing is we're proving that what our algorithm does and what we've stated is that on every subsequence, our subsequence regret will be root t, root capital T. And then I claimed that like, if you're a little bit more careful, you can actually get for every subsequence, root the length of that sequence. And so what that means is that, in some, like you can't improve this lemma, basically. Like, if all you know is an upper bound, so like these subsequence indicator functions, the ones corresponding to internal regret, they're disjoints. Because on the days when you played action 1, you didn't play action 2. And so, if your regret on the days when you played action 1 is like root the number of days you've played action 1, and your regret on the days when you've played action 2 is like root the number of days you've played action 2, somehow the worst case is if you play each action a 1 over k fraction of the time. And that saves you the square root k. So getting the better subsequence regret bounds is what you would do to get the better swap regret bounds, but we didn't do it. To use a better no regret algorithm in the outer. And then it all follows directly. Okay. So, let's do it. Let's look at our swap regret. If we look at the sum over all of the rounds of the difference between our expected cost when we play action AT compared to how well we would have done had we played action 5 AT. Well, an expectation is just a sum. So I can write this as the sum over all of the actions of the sum over all of the time steps of, well, what's the expectation? It's the probability that I play that action times the cost I experience when I play that action minus the cost I experience when I play the action suggested instead by the strategy modification rule. But this is just, if you look over here, this is just the regret on the subsequence for which you've played action A. Okay, so it's the regret on the subsequence for which you've played action A to what action? To action phi of A. But remember, what it means that you have no internal regret is that for every A and for every I, this sum is at most alpha. So we're just instantiating that for this A and for this I. Okay, so each of these expressions is at most alpha, so the internal regret bound is that tells us each of these inner sums is at most alpha. This whole thing is k alpha. Okay. So what? Well, we know how to get internal regret directly. We just instantiate our subsequence regret algorithm with a particular collection of k subsequences. What regret bound is it going to give us? Our regret bound depends only logarithmically on the number of subsequences. So it's going to give us a regret bound that is like, you know, our regret on each of these subsequences will be like square root of t times log k. Okay, that's our internal regret bound. And therefore our swap regret bound will be square root of t, k times square root of t times log k. Okay, so we still, you know, we don't, this is not the, you know, as we mentioned, if you work a little harder, you can turn that k into like a square root k. But we still have the right dependence on t. It's like a root t bound, which means that if in an arbitrary game, if all of these players play the game using the subsequence regret algorithm we derived today for this particular collection of k subsequences, then in, you know, like 1 over epsilon squared, or maybe k squared over epsilon squared many rounds, they will converge to an epsilon approximate correlated equilibrium. Okay, so sort of an analogous statement to what we said about players playing multiplicative weights in 2-player zero-sum games. They converged in like 1 over epsilon squared many rounds to approximate min-max equilibria. Except now we don't have to assume that it was like a 2-player game or that it was a zero-sum game. This statement applies to any game. The convergence time is actually totally independent of the number of players, right? Like, you know, we just need each player to have small swap regrets, and we just gave an algorithm that'll guarantee it in sort of, you know, epsilon swap regret and on the order of 1 over epsilon squared many rounds, no matter what the costs are. In particular, still works if the costs are generated by the collective actions of your n-1 opponents. And so we get sort of a, in an arbitrary game, a simple dynamic that converges to correlated equilibria in a number of rounds that depends polynomially on the number of actions and how closely you want to converge, and it's totally independent of the number of players, which is kind of remarkable. Okay. So that ends our subsequence regret section. We'll do something new next time. Yeah.
Because instead of swap regret that led to an efficient algorithm.
That's right. Yeah, there's k to the k swap functions, which might have scared you. But there's only k internal regret sequences.
And that general algorithm is k internal regret sequences exactly to do someone
It's a good question. I sort of think the answer is yes, because they look so similar, but I actually haven't verified that. Like, so when you write down this matrix, if you're me, it gets a little confusing. Is this really like a stochastic matrix? Certainly morally the same algorithm. Whether it's literally the same thing, I'm not sure. But if you figure it out, I'd be happy to know. All right, I'll see you guys on Wednesday.